Linear maps in the matrix. So these are the outline. This is a long chapter. We'll take a break in the middle, looking at interlinear maps, skew target boxes, then spend a good bit of time on the matrix form. I'll do a lot of stuff that wasn't in the book as a bit of review for those who might not have remembered any of that from high school. Then we'll spend time on linear spaces, scaling, reflection, rotation, shearing, projections, all this stuff. Areas, determinants, maps, compositions, and a little bit more on matrix multiplication just as a reminder. So we're looking at linear maps. So in 2D, which is where we're going to start, linear maps are things like rotation and scaling. So if we apply it to a square, the outer black square here, I might rotate it and scale it a little bit, and then I get the white square. And then I can rotate it and scale it again and get the next black square, and rotate it and scale it, get the next white square, and so on. So this idea of taking a shape and applying a linear map to it gives us a particular way of transforming space. And the geometry really of anything has two main parts. Something we described as the object, the square in this case, and then how these objects can be transformed or changed over time, the transformations that led to the white square, the next black square, and so on. These transformations are often called maps, and they may be described by the tools of matrix operations. In particular, linear maps can be described as matrix operations. The form of matrices were first introduced by Grassmann in 1884 and became the basis for the topic of what's called linear algebra. There are, of course, more complicated kinds of maps. They're not always going to be linear, but what we'll look at in this class will be linear maps. We actually already introduced these a little bit when we talked about this in Chapter 1, where we looked at local coordinates and global coordinates. There we had transformations, but all they were scaling and translation. So this time we're going to look at things that include rotation. And so we're going to go back to our coordinate system, and we're going to think about this idea of revisiting how the unit square can be mapped into a rectangular target box. So if we think of our unit square, we can view this now as a map. We're going to take our unit square divided by two coordinate vectors, E1 and E2. And in that, after we do some transformation, a vector in the E1, E2 system always exists as V1 times E1 plus V2 times E2, where V1 and V2 are just the coordinates of our vector in the E1, E2 system. If I now think of mapping it, I'm going to transform it to some new space. I can map that to some vector v prime, which is v1 a1 plus v2 times a2. So that is, if I were to take this same point, v, and instead of looking at it in the e1, e2 coordinate system, I looked at it in some other coordinate system, it would have a different position, right? The vector would be different in that new space. Notice that in this drawing here, a1 is longer and a2 is much longer. So what used to be a simple vector v became a much longer vector over in this transform space a1, a2. And don't worry about what the drawing is right now. We're going to come back and we're going to go through this a little bit more formally. So let's see how we can do this. So let's think of our a1, a2 coordinate system as having the origin and then being defined by two vectors, a1, which is 2, 1, and a2, which is minus 2, 4. Okay, so we now have two new vectors to define our coordinate system instead of the normal unit vectors of 0, 1, and 1, 0. So given that we have some v equals 1/2 and 1, this v here, in the E1, E2 coordinate system, we can now ask what will it become in the A1, A2 system. And it turns out we can do that by looking at 1/2, the first coordinate of v1, times 2, 1, plus 1, the second coordinate of v, times minus 2, 4. And that'll give us a new position, which is minus 1, 9/2, which just turns out to be what this vector here is showing. So in this new coordinate system, v1 has the components 1, 1/2 with respect 1/2 and 1 with respect to the a1 coordinate system. It has the v prime has the component minus 1, 9/2 with respect to the e1, e2 coordinate system. So these two vectors live in two different coordinate systems, and we can transform back and forth between them. And these have a much more complicated mapping, and we'll talk a lot more about how we get through those kinds of mappings as we go through this. But you might notice, for example, that the scaling was taking the coordinates in one space and multiplied by the vectors that came from the definition of the other space. And that's going to be a big part of how we do it. Now, if we start doing this with all these vectors and stuff, it gets to be a little complicated. So we're going to introduce more compact notation to make a lot of this easier. So we call this representation the matrix form, And we're going to think of everything as having a double set of subscripts. So I can think of the vector A1 as actually having two components, as being written as A1, comma 1, A2, comma 1. Just like we originally wrote the vector V as V1, V2, here I'm going to write something that already has one subscript, A1, as A with a first subscript for its row and its other second subscript because it came from A1. So this gives us a way of looking at it. So if we go back to the components for V1, I can start writing that as minus 1 9/2 equals 1/2 times 2 over 1, the vector 2, 1, plus 1 times the vector minus 2, 1, which we can write in what's called matrix notation as the vector minus 9/2 equals the matrix 2 minus 2, 1, 4 times the vector 1/2, 1. In this case, this is a 2 by 2 matrix. It has 2 rows and 2 columns. And the columns are the vectors of A1 and A2. And this column space will be something we'll use lots of times. Okay, so we've briefly introduced to this idea. We're going to go a little bit beyond the book and talk a little bit about the matrix algebra. And I'm going to actually generalize, because I actually think it's easier to keep track of these things in more general spaces than just 2 by 2. So this idea of subscripting, I can think of it in a more general space. I can think of a matrix A as having m rows and n columns. And when I index them, I write A sub row, comma, column, A sub 2, 1, A sub 1n, A sub mn. Those give me the elements of the matrix, indexed first by row and then by column. Okay, so that's doubly subscripted array of elements put together. For those of you think of this in computer science, this is a two-dimensional array, right? And I can index it first by rows and then by columns. Okay. Inside that matrix, I can actually think of a very special case called the row vector, which is a 1 by n matrix. A, which is just has got, and because it only has one, we sometimes get drop the other component and just write A sub 1, A sub 2, A sub n, which is A sub I. It's a row vector. We can also write a column vector, right, which is what we actually have been calling vectors, or just column vectors, A1 through AN vertically. Notice this can be a little bit confusing. If I just said A sub I, do I mean of a row vector or a column vector? In context, you might be able to figure out what they are. Very often, I will stand for the row and J will stand for the column, and you can put those two together. Now we have a bunch of terms. In fact, we have a lot of terminology throughout this entire lecture, so please do make sure you know what these terms are. I can almost guarantee there'll be quizzes and exam questions where you will be asked to define these or show examples of what these definitions mean. So the first of these is the definition of a transpose of a matrix. Okay, so, and this is obtained by interchanging the rows and columns. So if I had the matrix 1, minus 2, 3, 5, then the transpose of that, generally written in our textbook as A sub t, or A sup t, is 1, 3, minus 2, 5. You'll see the 2 and the 3 swapped places, the 1 and the 5 stayed where they were. In fact, since we can think of a vector as a column matrix, then I can also talk about the transpose of a vector, and I get a row vector, minus 1, 4. Okay? And there's some nice identities to play with respect to transposes. If I take the sum of two matrices and ask for its transpose, that's equal to the transpose of the first matrix plus the transpose of the second matrix. If I take the transpose twice, if I sort of flip something left to right and then right to left, I get it back again. So I get the same matrix. And if I multiply by a scalar, it doesn't change the transpose. So the transpose of a scalar times A is the scalar times the transpose of A, which you can sort of see just by looking at that. Of course, in the more general case, we can think about, again, rows becoming columns and whatever, and we can write A and A transpose. And I'm going to just show you that you got to be a little careful when you read other math papers or other textbooks. You might see them use A prime instead of A transpose. For example, when we work in MATLAB, it will use a single quote to mean transpose because typing the superscript T is too much of a pain to be typing. Okay? And then we have another specialized term which we call a symmetric matrix. And a symmetric matrix means A is equal to A transpose. So if A is equal to A transpose, can the matrix have different numbers of rows and columns if it's symmetric? No. if it's A is equal to A transpose, then AM1 is going to have to equal to A1n, which means M and N are going to have to be the same. Okay, so you can only have symmetric matrices if they're square. And as soon as they do that, you have actually this relationship that the things that are across from each other, A12 and A21, will be the same in a symmetric matrix. Okay, so now we've defined a little bit of terminology. Now let's go look at some operators, which are a lot more fun. What can we do with matrices? So the first thing we can do with matrices is add them. So if I have a 2 by 2 matrix A and a 2 by 2 matrix B, then I can get their addition. Now to do this, they have to be the same dimension. So if they're 2 by 2, of course they're the same dimensions. In the higher dimensions, we have to make sure that they're exactly the same shape, which is what we'll often call the shape of a matrix. So then what we do is we add them element-wise. So of this 2 by 2 matrix, we have the first element is A11 plus B11. A11 plus B11. Then A12 plus B12, and 21, 21, 22, 22. So we get a 2 by 2 matrix. Now, one of the things we'll see in terms of matrices, as soon as we start looking at matrices and vector products, is that they have what we call the distributed law. A matrix times a vector plus another matrix times a vector is the same thing as adding the two matrices, and then multiplying by the vector. And that, of course, can actually save us some computation, which we'll see in a little bit, because adding and then multiplying will be cheaper than multiplying them twice and then adding. So now we're going to start talking about the product. The first product we've actually already seen. If A and B are two vectors of the same size, right, same length, A11, B11, B123, then we've talked about this idea of what's called the scalar product or the dot product, and that's obtained by taking the two elements and taking the corresponding product of their same elements. So we're going to take the first two elements times each other, the second two elements times each other, the third two elements times each other. Now notice that a little bit like addition, that's doing it sort of pairwise. So the dot product of two vectors is going to be interpreted as the pairwise product of each of their elements. Okay? But it becomes a little bit more complicated when we move beyond vectors. So let's move to the next simplest case, a vector and a matrix. So I have a matrix A and a vector V. Then we're going to define that as V1, the value of V1, times the column vector A1 that came out of A, plus the value V2 from the component V, from the vector V, times the column vector of A2, which you can see gives us a vector V1 A11 plus A2 V12, okay, V1 A2 plus V2 A22. So the result of this matrix times this vector is a vector. And we can relate that back to the dot product. In fact, the matrix A times V, so here's the matrix A, here's the vector V written as a column vector, and we can see that this is really the corresponding, this is the dot product between the corresponding row and the column vector. So I take the row 0, -1, dotted with -1, 4, and I get the first element. Now, many of you may find it a lot easier to think of this graphically, so I'm going to write them out this way. I'm going to take this row from the matrix and the vector, I'm going to write them. Notice I've written them first. The first thing you write down is the first thing of the product. The second thing, where you go up, is where you write the second element of the product. And I'm going to get this. I'm going to get this dot that. So row dot column equals the value -4. And I'm going to put that down here for -4. I'm going to do the same thing now with the second row. Second row dotted that column. And I'm going to get -14. And so this gives me the same product I got right here. Whoops, back too far. This dot that gives me -4, this dot that. Here you have to remember to go over and down, over and down. The graphical form of writing them in this sort of table sometimes makes it easier to remember which way you're going. You always go across this side and down that side. First thing of the equation, second thing of the product, and this then will give you the values. For 2 by 2 or 2 by 2 vector times a vector, not a big deal. Once you start getting bigger ones, we'll see how that becomes useful. Okay, a little bit more matrix terminology. We can talk about the diagonal, the elements A11 and A22 form the diagonal of the matrix, and in higher dimensions it'll just be the things down the middle of the matrix. If we have the matrix A times V, then V is the pre-image of V prime, and V prime is the image of A. We call it the image. We're going to take A as a map. We're going to map V to the image V prime. Okay. The space in which V lives is called the range of the map. The space in which the space in which V prime lives is the range of the map. The space in which V lives is the domain of the map. So we're going to map from the domain into the range. So once you get home, or once you get done, you've mapped into the range because you want to be home on the range. So you're going to map from the domain into the range. And then we'll also talk about something called the column space, which is all of the V prime that can be formed as linear combinations of A. And for now, we'll come back to that again later, but for now, those are just some more terms. Diagonal, image, pre-image, range, domain, and column space are all things you should know what they are. Okay, so I'm talking a little bit more general about matrix multiplication. The book sticks with 2 by 2, but again, I find some of this easier to see when we go to non-square and bigger sizes. So if I have a 3 by 3 matrix A and a 3 by 2 matrix B, I'm going to multiply, again, I'm going to view this as the dot product of this row with this column, right? So here I'm going to have the dot product of 1, 2, 4, that row, dotted with minus 1, minus 3, 1, that gives us minus 3, and that's the first element of our dot product. So the general, I'll then take this row, dotted this column to get 10. And 915 dot minus 1, minus 3, 1 to get minus 7, and so on. And we'll do a couple of examples in a second. Now notice that this wasn't square, so now I have to be a little careful, and this actually, we have to make sure that if we're going to define multiplication of a product, we have to have the same shape on the inside. So I have an m by n, m rows by r columns, times something that is r rows by n columns, and the result of that product in general is an m by n matrix. Okay, so you got to match up the two insides, and then the outsides tell you what is the resulting size of the thing. Now, just as we did with a vector, I actually find for many of you, if you're not that comfortable with matrix multiplication in the beginning, you might find it easier to think about it in the more general case of, if I'm going to multiply A times B, A is in this case 4 by 2, times B, which is 2 by 3, then I write it down and I go across this, down this, so I'm going to do the dot product of this row with this column to get this value, and this row and this column to get that value. So what would I do to get this column down here in the lower left? I do the last row times the first column. Okay, so what do you see in this one? Okay, I've already highlighted that this row and this row produce, this row time dotted with this column give us this entry. And overall, what's the shape of A? It's 3 by 6. What's the shape of B? 6 by 4. The shape of 3 when we get done is 3 by 4. Notice that, in fact, the dimensions don't have to stay about the same. They can become much smaller. So a 3 by 6 matrix times a 4 by 6 matrix yields a 3 by 4 matrix, which is what we have in this example. Now, when we drew that in sort of the tableau form, right? We do this. One of the things to note is that when we go to do this, we're actually going to use the same row and the same column multiple times. So I'm going to do the dot product of this row with this column, the red one, red row, times the red column to get the red cell in the output. I'm going to take the same row, blue row, so it's the same row, but now I'm going to call it blue just so you can sort of see when I take it dotted the blue column, I get this output. Okay, and that's normal in matrix multiplication. When we're doing the multiplication, we're going to use the same row multiple times, the same column multiple times to get our outputs. Okay, now we have a couple other special terms I want to introduce. The first of these is the identity matrix. It has some nice properties. The identity matrix is a square matrix, so it has the same number of rows and columns, where the diagonal is all ones and everything else is 0. the identity matrix is generally written as the capital letter I. Sometimes it'll be I with a subscript to tell you exactly how many rows and columns it has. And it has a very special property that the identity matrix, when multiplied by any matrix, gives you back that matrix. So A times I equals I. Now, are there any constraints on I? Well, whatever A is, let's say A is M by N. Then what identity matrix is I? Well, it has to be an N by N matrix, so that I'm going to take an M by N matrix times an N by N identity matrix, and we get back my M by N original matrix. Okay, there's another very special matrix, the zero matrix, and the zero matrix is sort of absorbing. So when I multiply A times the zero matrix, I get the zero matrix. So once you interact with it, it becomes a zero. Again, to maintain the rules of multiplication, the zero matrix needs to be the same shape so it can be used properly in the matrix. Now, there's some other properties we get out of this. The first and the most non-intuitive, so it's important that you get this because this is not how numbers work, is that matrix multiplication is not commutative. The order does matter. A times B is not equal to B times A. And that should say the order of multiplication does matter. It may be that the product, in fact, of AB exists, but B times A doesn't even have to exist. It's not that it's not equal. It doesn't even make sense. So, for example, if we looked at before, we had a matrix that was 3 by 2. So if I had something that was 3 by 4 times something that was 4 by 3, when I go to convert B times A, I'd have something that was 4 by 3 times something that was 4 by 2, and I can't line them up. They won't work out properly. Okay, so it doesn't have to be the same. So non-commutative is very important. You got to keep these in the right order. But it does have some other properties that we are sort of used to from other things. It is associative. So if I have three things, A times B times C, that's the same as A times B times C. And I can put the parentheses and do BC first or AB first. It doesn't matter. It's also distributive. So if I have A times the quantity B plus C, that's the same as A times B plus A times C. And similarly, B times C quantity times A is the same as AB plus C times A. I've already shown you the identity matrix. In fact, the identity matrix can go on either side, although it might be, if A is non-square, then it'll be two different identity matrices. A times I will give me A. I times A will give me A. And the same is true with 0. Again, the size might be different depending on what size it's on, but A0 is 0 and 0A is 0. And then the transpose operator, if I take A times B transpose, that's equal to B transpose times A transpose. Notice this is a little different than from addition, where we had A plus B transpose was A transpose plus B transpose. Here, you got to remember, when you take the transpose of the product, you not only swap the data up and down across the diagonal, you swap the two matrices that you were taking part in this. Oh, you know, haven't given you enough terminology, so let's have a little bit more. The rank of a matrix is the number of linearly independent columns or rows of the vectors in the matrix. We'll talk about that. For a 2 by 2 matrix, defining an A1, A2 coordinate system, we're going to call it a full rank. It's of 2. Full rank means it has the rank is the same size as the matrix. That means that the columns A1 and A2 that we're trying to map to are linearly independent. And that's another way of thinking about it. A matrix is full rank. When I map it, all of the dimensions remain because all of the new columns are linearly independent. A matrix is rank deficient when it does not have full rank. So if A1 and A2 are linearly dependent, so they're parallel vectors, then the matrix has rank 1. We also call that a singular matrix. If you lose rank, it becomes singular. There's only one matrix that has rank 0. That's the specialized 0 matrix. Mr. Smith absorbs all. He's the only one you can have. And in general, in fact, that's why we set up here linearly independent columns or rows. The rank of A and the rank of A transpose are equal because the number of linearly independent rows and columns turns out to be the same. So, going through a little bit of the basics, some exercises. These are from the back of the book, so you might want to work through some of these. Make sure you're ready. We will be having a quiz in the next class. So, given some matrices, vector, be able to do things like what's a linear combination of these vectors that result in that, write it in matrix form, be able to use those matrices, be able to do things like express equations in matrix forms, know if a vector is in a column space, be able to answer questions like, is it symmetric, what's a transpose, what's the transpose of this matrix, that matrix, compute some very basic addition, subtraction, multiplication, answer questions about rank. There's a lot of terminology. All that's fair game. Last thing you may want to do, here's a matrix multiplication example. This is a practice example. It's not in the book, but I want to make sure you really have matrix multiplication down. So here's a practice example. I'll actually go over this in the next video, but before you jump ahead, go through this, work it out, make sure you know how to do all of the computations necessary to do this. And with that, we'll call this intermission. If you're not sure about how to do the matrix stuff, you want a little bit more practice, want to see some more examples being worked out, then I recommend you go down to the Khan Academy. They have lots of matrix examples worked out in the Algebra 2 section for high school students. So that's it. See you in the next video.